Good evening and welcome to ML Ticket. Uh, we are now revising all the topics that we have learned through the last from the last few sessions, and today is our last session that we will conduct on machine learning. To give you a brief idea, we have covered a lot of things inside of the beginners machine learning uh, tutorial that we have seen. We have considered a regression problem, precisely a California regression problem, and we have tried to build a model so that we can predict the median house value. So apparently we have done this, and apparently we are successful in doing this, and I have shown you all the processes, all the techniques that needs to be done, all the uh, things that needs to be taken care of while doing the machine learning project. So let's get started. Pardon if you are hearing some noises, I cannot help it apparently. Yeah, the guy is outside is a pretty disturbed right now. So let's continue. So today we are starting with the last topic of the evening, and of course of the session, that is the and that is a part of the machine learning. In the previous two session on revision, we have covered the data visualization and data pre-processing, and today we are going to cover the machine learning part. As there are, let's start from the beginning. This is the most basic question that you should ask whenever you are starting a project, that what type of learning that you are actually addressing at that point. Okay. So if we are given a machine learning problem statement, you should first think that you should come to your mind, Jay, what is the type of learning that I should use? Is it a supervised learning problem, or is it an unsupervised learning problem? Is it a semi supervised learning problem? Is it a reinforcement learning problem, or is it something which is related to deep learning? So apparently we have not gone into the we have not talked much about the semi supervised reinforcement and deep learning, because to be honest, this is not a intermediate or advanced machine learning thing. This is a way, these things are way too advanced. So we are only concerning ourselves with the supervised learning problems. As a beginner, you can just stick to supervised learning, and to be honest, let me tell you, you can build some amazing stuff using supervised learning. But I don't even think the supervised learning is very uh, slow, or it is backdated or something like that. Okay, so supervised learning is good enough for you to understand right now. Okay, so let's talk about supervised learning. We have seen what is a supervised learning. So supervised learning is just when the data is labeled. When the data is labeled, we call that learning in supervised learning. Okay, so we can see here, the input data is called training data, and it is and has known label or result, such as a spam or not spam or stock price at a time. So you know what data set you are dealing with. So at that point, it is better to use supervised learning. Another form of another learning is to unsupervised, which is exactly the opposite of supervised learning, and that the input data is not labeled. To be honest, I don't want to get too. I don't want to get into the depth of unsupervised learning, because this is way beyond our scope. So there are some common machine learning algorithms that we can see, and as a beginner you should, I won't say master, because it is a too vast a topic for you to master every and each and every algorithm. But I would like you to master some of these algorithms. I would like you to I'm going to in a go through linear regression, logistic regression, decision tree in a way deeper manner. Because if you just get cleared with the basic algorithms now, you can easily get all the advanced stuff that you can build, all the advanced algorithms that we have seen. Okay, so these are the most common algorithms. Okay, there are many algorithms that you can use, and almost every algorithm which is in machine learning is implemented using scikit-learn, so you don't have to worry about that thing. You just need to understand that where to use what algorithm. And to be honest, this is the most debatable thing that we can do right now. So as a beginner, you should not concern yourself, with what algorithms to use. I would say just brute force over every algorithm that you know. Okay, and see what results you get. The more you build projects, the more clarity you will have, what algorithm to use in what situation. Okay, though you can learn a few stuff, with a few uh, things which will help you to determine the algorithm, but at the end of the day, it just depends on your practice. So the first thing that we learned that is the linear regression. Linear regression is just the most basic and most easiest algorithm to learn when you are doing a machine learning project. Basically, it is the linear regression is represented by the mathematical expression y equals to mx plus c. As a science student, you should have at least heard about this thing, y equals to mx plus c, that where m is the slope and y is the y-axis, x is the x-axis, and b is the what is the intercept. Okay, so basically I don't want to get into the details of this linear regression. You can just read about this online, and to be honest, we have dedicated our entire session just for linear regression. So if you want to uh, get back to the basics, get back or have a detailed discussion about this, you can just refer to that video so that you can understand. Okay, you can just read through these things. There is nothing much to say. Basically, it is a straight line. Okay, it's a straight line, and things are all the data points are plotted according to that. So next comes the decision tree. The decision tree is represented using just a tree format. Okay, so if you are familiar with graph theory, it is really easy for you to understand what is a decision tree. Otherwise, you may have to struggle a little bit about understanding decision trees. Otherwise, yeah, I would suggest just I'm pretty sure that you have read your graph theory, but some of you may not remember your graph theory. So I would just suggest you to go through the basics of graph theory once and then come back to the decision tree. It will make your life way more easier. So uh, as we can see, the decision tree, as I've discussed earlier also, that decision tree is way more complicated machine learning algorithm than linear regression. But it is not always a good choice. Okay, linear decision tree is not always a good choice, because if I go back to the code that we had. Okay, not here. I am just going for the final comparison that we made, right? I think it is here only, right? Yeah, this one. So this is the final comparison that we made for the decision tree and the linear regression. Okay, so here we can clearly see that though our decision tree is a much complex algorithm, our decision tree is so badly overfitting our dataset that our underfitted linear regression model is working way better than, not way better, but it is working better than decision tree. So there is no actually hard and fast rule that if you use more complicated algorithms, you will get better results. There is no hard and fast rule about that. But this is a proof that you can see that linear regression is a very simple model, very simple, for mathematical formula that you can use. We have been learning y equals to mx plus c from class 8, I guess. Okay, so and decision tree is a very complex model, if in comparison to linear regression, but it works. It does not work very well when it is in this case, in this particular scenario. Okay, so this is a proof that you can that you can understand the it is there is no such thing, the more the complicated, more calculated algorithm you use, the better results you will get. So this is not the way you should think. You should you should, sometimes you need to just do trial and errors, and sometimes you need to learn the underlying learn the underlying things of that algorithm, what that algorithm requires, when to use that algorithm, when does the algorithm works very good. So you need to understand your data more. Maybe you should have maybe you have to do much more visualization to understand your data before applying any algorithm. So these are the things that you should be concerned about. Okay, so I am not another thing. Okay, I think we can I will be talking about that. Okay, so overfitting the data, as I said, Jay, if you're over generalizing the data. Okay, suppose your data sets, the model is over generalizing. It is working so good on the training data that when it is exposed to the testing data, it does not go good accuracy. But when it is exposed to the training data itself, it is coming up with 100% accuracy. So in this case, the data is overfitted. Okay, okay, so and the opposite of overfitting is underfitting. I don't need to explain what underfitting is. When when our model is too simple and it cannot understand the underlying structures of the dataset, underlying features of the dataset, and we have to point out those things, every each thing into to that particular a particular model, that at that point the model is underfitting. So underfitting and overfitting is sometimes confusing. And to be honest, when I was learning about this and when I first heard this underfitting and overfitting, it was very confusing for me, and it really took me a while to understand these things a little bit clearly. And there is no hard and fast rule that will tell you that the data is underfit. There is no library or something, some metric that will tell you that the data is underfitting or overfitting. You need to apply your common sense. You to try out different metrics of different accuracy metrics so that you can understand. So basically, we have chosen the RMSE as our accuracy metric. To be honest, there are so many metrics that you can use that I if I start listing them out, it will take another 1 hour. Okay, so I'm not going to list everything out. I'm not going to list everything out, but we have used RMSE in this project. But there are numerous way to check accuracy scores, and I would like you to go through some of the accuracy score. You can just search this very thing in the Google, and you will get so many results. Okay, so RMSS is the one of the most standard way to check accuracy. That's why I used, and to be honest, it is very easy for you to understand also. If I use ROC curve or F1 score or different things like this now, so you will get a little bit confused, or you may not understand, because I had to explain you the math behind it. And RMSE, to be honest, it's a little bit easier for you to understand. That's why I considered RMSE as our accuracy metric. Another thing that we talked about is the training accuracy, testing accuracy. Okay, so as we have seen, as we have seen that if we do this, there is a higher chance of overfitting the data, and hence it is not good measure of accuracy. Training accuracy is never a good method of checking accuracy, because if you're training the data, if you're training a data on a data set, and you're taking data points from that same data set and checking it checking it, you may get a overfitting result. And to be honest, this is not a good way to check your accuracy. So training accuracy is a no-no for you. The most of the people that do, most of the people do is a testing accuracy, that they divide the data set into training set and testing set, and use the testing set to get the particular accuracy. But it also comes with the problem of high variance estimate. What is that? As we have seen, I don't think we can code this anymore right now, but let me get back to the point. Yeah, like this one, like this one, that we have this is the testing accuracy, like we just making a prediction over the test set, right? So we gave it a random state of 56 and we are coming up with 94% accuracy. But if I change the random state, it changes the accuracy score. So it is highly dependent upon the way the data set is being distributed, or what data points are in the testing data set. Okay, so though it is a good measure, to be honest, when I started, this was I never thought that there is any other way to check accuracy score. I thought this is the most optimal way, but apparently it is not the optimal way. But as a beginner, you can just check this out. If you just limit yourself to the testing accuracy only, so it is not a big deal for you, because it won't make a hell and heaven difference. Okay, and the 94 can go, if you can take another random state, the 94 can go to 98. Okay, so nothing nothing very significant as a beginner. But I would say this is not a good practice to use testing accuracy, because we have a good metric to use other than testing accuracy. And what is that? That is k-fold cross validation. So this is the algorithm that k-fold cross validation follows, that it divides the data into k equal partition. We dedicated an entire session for k-fold cross validation. If you want any kind of clarity, just go through that session, you will get the heck of it. So basically, this is how our k-fold cross validation works. It divides our data and into partitions, and take a chunk for training and another chunk for testing, and it does this for every set, and we get 5 results. So some of the recommendations for cross validation is it can be that the cross validation should always, in k-fold cross validation, we should always consider the value of k as 10, because it is experimentally seen that it is the best value. If you want to read more about that, why we are considering k equals to 10, because most of the cases, whenever you are looking online, you going through other people's code, you will see, and they are using cross validation, you will see that the k value is always 10 in k-fold cross validation. And you may wonder why, and that this is the reason, because it is experimentally it is found that k is equals to 10 is the optimal value. Of course people change it, according to their use, but when doing a plain and straight cross validation, we use k equals to 10. Another thing is that it uses stratified sampling. If you remember, we used stratified sampling in our data set, and this is the not this is the reason why you used stratified sampling, but this was one of those reasons. Another thing is the scikit-learn comes with a cross library known as crossval score, which does everything that we have discussed under k-fold cross validation, and you don't even have to worry about it. Okay, so I think that is pretty clear. Pretty clear. We used k-fold cross validation. We saw k-fold cross validation over a data set known as Iris, and then I applied that to our own data set of a housing median housing, to get the housing median value. And to be honest, it turned out to be very good very good at some point. We also cross-checked all kinds of values, and then we also trained a random forest regressor random forest regressor, which is as a random forest is nothing. I have said this many a times that the random forest is consist of many decision trees. Many decision trees make up a random forest. Okay, and it's like many trees make up a forest, right? It's like that. That's why the random forest, the name came from here. And we saw that it is giving us a greater accuracy. That's why we used random forest. I would again say, Jay, as a beginner, you can just stop at this point. You can just look at the score, RMSE score, or any kind of score that you are using, any kind of accuracy metric that you are using, and you can just stop here. And but as we are, as I said, Jay, I will be discussing something about fine tuning your model. Um, you can go for this grid search CV. Another thing that I would say, Jay, as a beginner, I won't suggest you to use this grid search CV because apparently you won't be able to understand what values to give into this range. If you give every possible value, from if you select a range from 1 to 100 for an estimator's max value also 1 to 100, it will take forever for you, for your model to just get your estimator. It is not wise to do that thing. Okay, and you are basically brute forcing every possible values, every possible hyperparameter. You are checking every possible hyperparameter inside your model, and that is not a wise thing to do. But since we are talking about fine tuning your model, I would say that if you are fine tuning your model, use cross validation. Use run a for loop and check all the cross validation scores that you are getting and choose the optimum path, because you as a beginner you should only do that. But as you start doing many projects, you will understand that what values to give into these hyperparameters, that in estimators, bootstrap, max features. You can just read the algorithm, you can just read the algorithm documentation so that you can understand this hyperparameter. I'm not going into it, but I just showed you this just to make sure that yes, just to tell you that this kind of things exist in our machine learning thing. We could use this. It's a very good feature when you know what values to use. Okay, the grid search CV and hyperparameter tuning. This particular thing is known as hyperparameter tuning, by the way. And there are multiple methods you can use, but I showed you only one, that is the grid search CV. um, and basically it will and if you just do a best estimator, it will give you the uh, algorithm along with the hyperparameters, and you can just copy and paste it. As you can see, I can just copy it and paste it, and we got a good accuracy, right? And it was not a very drastic change. It was like 52,000. We got a 52,000 mean before we tuned our hyperparameters, and after tuning our hyperparameters, we got a accuracy score, RMSE value of RMSE mean value of 4,900. It's not that great, okay, but still, you are getting a little bit of RMSE, little bit of accuracy score, little bit of increased accuracy. And in case of Iris, we also saw that we did hyperparameter tuning now by using we used hyperparameter tuning, but we used cross validation where we just ran a for loop. You can go back to the session to get a detailed explanation of that. We ran a for loop, and our accuracy score jumped from 96% to 98%. So 2% jump is a lot. Okay, so basically this is the end of it. And it was really great for me, and I enjoyed it a lot. I hope that you people also enjoyed, and thank you for giving me this opportunity for so that I could share my little knowledge that I had. And of course, I would like to thank Alisha Shaw, the head lead of DSCPIB, to give me this opportunity, wonderful opportunity for me to spread my knowledge. And it's been great. I'm really I'm really pleased that she gave me this opportunity, and of course, all the other DSC members who helped me to arrange these meetings and help me with the Instagram posts and or everything, registration and all. Apparently, I don't know everybody, but my earnest gratitude is towards everyone, of course, and of course Neha Sahu, who recorded all our sessions and uploaded these things on YouTube so that for future reference you can get these things. I'm really grateful to all of you. So thank you. This is Siddhartha Addi, and for the final time, I am signing off.